Hello and welcome back. We will prove that for the case of pure bending, we have the first moment of area about the CG will be equal to 0. The second expression is that the product of inertia will be equal to 0. This is a beam, but in the isometric form, we have set the x-axis as longitudinal axis and y-axis is perpendicular to both x and z. Both x and z axes are pointing to the reader. In case we have a pure bending, as we can see in the red arrow, this is rotating about z, so we'll call it m sub z. If we have a look at the transverse section, we will see the y-axis in the vertical direction and that z-axis will go to the left. We will examine small strip dA apart from the z-axis by y distance according to the expression which we have obtained that the strain equals minus y over r at distance y. The negative sign will indicate that when y has a positive value, we have a compression for the uppermost part of the section, while for the lower part, y has a negative sign and we have a positive stress value, which means that we have tension. The relation between strain and stress is that stress equals strain multiplied by E, where E is the modulus of elasticity. Please refer to the two sketches close to each other. Since we have pure bending and this pure bending is not accompanied by compression or tension, so it means that for the whole section we don't have any tension or compression force. The sum of the forces will be equal to 0. For that strip dA, which you have stress equals minus y multiplied by E divided by R, we will make integration for the whole section and we will equate it to 0. And since the stress minus y multiplied by E divided by R equals to 0, we notice that the E over R part has a value, so it cannot set equal to 0. So the only thing that would be considered equal to 0 is the integration of y multiplied by the A equals to 0. And this expression we are familiar with that one. It is the first moment of area about any section, which means that the section is passing by the CG. So from that relation, we get that the z-axis is passing by the centroid. In the next slide, the moment about Z equals the force by distance or stress by area multiplied by y. Since the stress equals minus E over R by y and area equals dA, then we can express that mz equal to the integration of f by dA by y, or the integration of minus E multiplied by y divided by r, all multiplied by dA by y, which can be simplified to the integration of minus E over r by dA by y square. We are familiar with dA multiplied by y square as the moment of inertia. In our case, the axis is z, then the m sub z equals to minus E over r I sub z. Multiply both sides by y, then we can say that y by m sub z equal to minus E over r multiplied by iz, which will lead us to the expression of the stress that F equals to m sub z multiplied by y divided by iz. Now, if we notice that we do not have a moment about the y-axis. If we write the expression in terms of stress, then m sub y equals to the integration of dA by stress F by the distance Z. Since we have an expression for the stress as minus E over R multiplied by Y, then we can rewrite the expression for the moment about Y as m sub Y equals the integration of dA by minus E by Y over R all multiplied by Z. On the left side, we have m sub Y equals to 0. And since minus E over R cannot be equal to 0, we are left with the integration of dA multiplied by YZ. And we are familiar with that expression as it is the product of inertia about the major axes Y and Z. And this is the second relation we are going to derive. SAP 2000 is one of the programs that can be used in structural analysis as well as designing. I have come across to a great course, CE160. I leave the link shown in the slide. The professor indicates both global and local axes and the difference in between. For instance, if we have a frame element as shown in the left side of the slide, selecting a horizontal member and enlarge it, we have three local axes, 1, 1, 2, 2, 3, 3. Local x 1, 1 is in the direction of the element, in the longitudinal direction, while local axis 2, 2 is perpendicular to both local axes 1, 1 and 3, 3. And it is in the direction of the minor x, while the last is visited by the girder portion and is rotating around local axis 3, 3. In the last slide, if we make an enlargement of the vertical element of the frame, we'll find that the local axis 1, 1 going upward in the direction of the global zx. The second local x 2, 2 is to the right. It is the same as the minor XYY for a steel section and is parallel to the global X for the last local X 3, 3. It is pointing to the reader, same as axis XX for a steel section and is parallel to the global XY. Thanks a lot and see you next time. Goodbye.